Oh, I took my car and I drove it off a cliff. What? How would you do that? For projectile motion. So what we're going to do here is we're going to look at projectile motion, and for our first example, we're going to look at launching an object horizontally, so completely flat, okay? Now, in projectile motion problems where we don't have air resistance, there's no external force once the object's in the air, we know that an object is going to travel horizontally at a constant speed. It's going to accelerate downwards due to gravity, but the horizontal component of that velocity is constant. Okay? So because of this, if we actually take our equations from our best friend, they'll actually boil down to this for the horizontal. That's just equation 1 right there. And in the vertical direction, we're actually just going to get this. And that's because VI in the y direction is going to be 0. We're going to see that momentarily. Okay, but for our demo here, what we're going to try to do is we're going to take a car, and this car is on a cliff, okay? And what we're going to do is we're going to take this car and we're going to drive it off a cliff. So here's the car. It's red because it's fast. Woo! And it's going to go off this cliff with some horizontal velocity. So this velocity is only in the x direction. Okay, and we know this cliff is at some height here. It's at some height h. And this car, we know once it leaves the cliff, it's gonna splat down here, break into a million pieces. What we're looking for is what is the range, or what is the delta x? How far did this car go? That's what we're looking for in this problem. Now, let's just grab some random values here. Let's just say that our velocity is 5.26 meters per second, and I don't know, what's a good value of height? Let's go with 30 meters. I don't know, let's just pick something. Let's just put something there, okay? So if this is what we have, let's go to the box and let's fill out what we know. We know initially, we know that acceleration for the x is always going to be 0, and it's always going to be negative 9.8 in the y direction. Okay? What else do we know here? We know the initial y velocity is 0 because it's moving just horizontal, and that means that this velocity here is 5.26 in the x direction. And remember, VI and VF are the same in the x direction, so that's what we're looking at. What else do we know? We know the car is going to fall from a height of 30 meters, so we can say that our displacement in the y direction is 30 meters, and be careful, it fell. It's a negative. Okay, so we're calling down the negative direction here. And since I've got 3 things on this right side of the box, I've got 3 out of the 5, I could go ahead and use my best friend. One of the common tactics we're going to employ is finding time on one side and then moving it to the other. And if we see we do this here, when I move it to the other, I'll get 2 out of the 3 things, which will allow me to look for my final answer of the range of delta x. So let's try to find the time here. Let's get that time, and if we can get it, we can move it and we can be done. Looking at this equation though, and the kind of the variables that I have, VI, delta x, and a, equation number 5 stands out very well to us. And that equation is the displacement, so delta x or delta y, however you want to write it. I like to just write it as delta x. That equals VI in the y direction times t plus 1/2 at squared. And what we quickly see is that in the y direction, since my initial velocity here is 0, this term goes away. And that's why what we have is just 1/2 at squared, and that's why up here we said this delta y, or the displacement, is just 1/2 times the acceleration squared, where that's gravity. So for horizontal problems, this will be your equation. It is just equation 5 though, with the initial velocity going away. If we plug in some numbers, we're going to see pretty quickly that negative 30 equals 1/2 times negative 9.8 times t squared. And now we just have to solve for this t. However you want to do this algebra is up to you. I like to multiply by the 1/2 first. So I get negative 30 equals negative 4.9 t squared. And then I divide each side by negative 4.9. This is very nice that the negative and negative are here because they're going to divide or cancel out. If they didn't, then when I took the square root of each side to get rid of that square for the t, I'd get an imaginary number, which is anti-bueno, okay? So 30 divided by 4.9 gives me 6.12, and that equals t squared. And then, like I said, we need to take the square root of each side to get rid of the squared. So the square root of 6.12, as we do this math, we get that the time is equal to 2.47 seconds. So we'll take that 2.47 seconds, we'll put it back up in here, so 2.47. It belongs on the other side too, 2.47. And now, on my right side, I have 2 out of my 3. So I can go ahead and use equation 1 over here. I can say that a velocity equals a delta x, a displacement, divided by a time. If I solve for delta x, that equals a velocity multiplied by a time. And in our problem here, this is just going to equal the 5.26 multiplied by the 2.47. And when I put them together, let's see, 5.26 times 2.47, I get 12.99, or let's just say 13 meters, which is about 39 feet, okay? So that is our final range on this problem, and that's what we were looking for. So it was kind of like 2 old problems. It was one with equation 5 and one with equation 1. But those are problems we can do. We know how to do those. We know how to put them together. We just had to do a little bit of algebra here. And really, our box guided us to find this solution. So that was a kind of neat thing that we got out of it. Now, this was a horizontal motion problem where we always know that the initial y velocity will be 0 and the the x acceleration and the y acceleration are always going to be 0, negative 9.8, but we really know that the y initial velocity is 0. But we could have been given other things. We could have been given other variables here, in which case, maybe we needed a different equation from our best friend. Maybe we needed to move things around in a different way. And we'll see those in some of the practice problems coming up. So with that, this problem here has been finished. I hope it was kind of straightforward for you. It's just stuff we've done previously, but just kind of doing it twice. And in our next videos, let's take some look at those practice problems. Let's dive in. Let's try to get them. Let's mess them up. Let's try them again, and let's see where we go. Okay, but for now, adios, and y'all take it easy.